Hey there, we're Stacks on Stacks, and our objective is to create a device that can stack money quickly.
If you've ever had to stack papers before stapling them, clean up after a night of Monopoly, or even stack a deck of cards, you're probably familiar with the issue that Brinks, our sponsor, is currently facing.
Right now, businesses drop notes into a Brinks safe. When the safe gets full, Brinks comes and picks it up. You've probably seen their trucks before. Finally, the money is brought to the processing facility where tellers run the notes through money counters. However, because the notes simply fall into a bag that sits in a bin inside the Brinks safe, these tellers are essentially getting bags of leaves. The tellers have to stack these notes by hand, which can get pretty tedious.
This is where our solution comes in. Brinks wants a money stacking device so notes can be processed more quickly than the current operation. By achieving this, tellers' jobs get a little bit easier, and so does cash management for businesses.
Now that we've provided some context and introduced you to the problem, we'll discuss how our solution came to fruition, the sorts of analyses and tests we conducted to validate design choices, how the final design might impact Brinks and relevant customers, and future work we would pursue. Beginning with the design specs, Brinks gave us some specifications that they want us to meet. These specs include single teller operation, compact size for desktop application, and a throughput rate of 333 notes per minute. It's important to state that the solution for automated stacking could have either been implemented into the Brinks safe, or what they call the B safe, or the solution could have been external, located at central processing facilities. In order to achieve these specs, required functions were defined. From the function tree diagram, a morphological chart was created, and consequently each team member contributed individual ideas for a solution. Finally, based off an evaluation matrix and the team's discretion, a design was chosen and prototyping of the tack-O-Matic commenced. As seen in the slide, the first prototype that was built, Prototype 0, was made of cardboard, and we tested shaking to move the bills by using our hands. We observed the money's behavior to the shaking funnel to gain an intuition of the flow of the notes, and this allowed us to determine whether this creative solution had potential. Through the proof of function testing, the team found that Prototype 0, with some design changes, did indeed have potential. A second prototype was made with plywood, and a drill linkage assembly was used to actuate the system. Testing was conducted to refine the actuation settings, namely frequency and amplitude, to maximize throughput. For the final design, engineering analyses were conducted in order to validate what was drafted in CAD. In this CAD model of the tack-O-Matic, a lot of the mechanical components can be seen, including the rollers at the front of the funnel, the belt connecting the gears to the rollers, the gear train itself, and various shafts on which these mechanical components are mounted. A motor and gear system is responsible for running these components. Good quality engineering analyses were required to select the right components and prevent any sort of failures or safety hazards. The team already had a motor on hand that was tested, but when that didn't work, the required specs were calculated to order an appropriate one. In the slide with the CAD models, the linkage or column that moves the funnel up and down was shown. Since this component has to support the weight of the funnel, a buckling analysis had to be conducted. The funnel's weight was found to be 3.15 pounds, and the max weight the linkage can support before buckling is 7.78 pounds. With the only additional load being bills, the linkage should have no issues with buckling. To ensure that there would be no severe deformities in any of the shafts, the team took a look at the shaft that bared the most load, which was the shaft with the small gear. The diagram shows that there is a force from the pulley, reaction forces from two bearings, the force from the gear, and the force from the linkage attached to the funnel acting on the shaft. The max stress was found to be around 3780 psi, while the yield for the shaft was just a little under 45,000 psi. Since the max stress of the shaft with the most load was nowhere near the yield stress, it was concluded that all other shafts would have no problems either. Finally, we had to analyze the gear teeth to make sure the gears we selected would work without any issues. Again, the true stresses fell below the allowable thresholds, which meant everything was okay. The final product was made of acrylic and plywood, with all of the key design features like the rollers and motor gear assembly fully implemented. Here's a video of how the tack-O-Matic works. Other aspects of the final design include a hopper, which allows the teller to dispense all the money from the bag at once, and a money receiver, which collects the stacked cash. As stated at the beginning of the video, the project's problem is the processing time of the money with the current process. Previously, Brinks had cassettes inside the B safes that would collate the bills as they were inserted. However, they eventually stopped using them due to frequent jams and increased manufacturing costs of the safes. But with a device that can achieve a throughput rate of 333 notes per minute, that processing time can fall back down to 7 to 9 minutes. This would allow Brinks to increase B-Safe sales by 5 to 7 times the current footprint. Money processing services would then scale up proportionally, but Brinks would not have to increase labor or facility size, clearly demonstrating the tack-O-Matic's utility. For the future, the team would like to make modifications to the hopper that would allow for better flow control. For instance, rollers or brushes at the bottom opening of the hopper could limit how many notes fall into the tack-O-Matic at a time. Also, to provide the motor with constant peak power, a wall plug would be ideal. As the batteries drain, the voltage supplied drops from 12 volts, so the motor's speed also drops. Lastly, the system for retrieving the stacked cash can be improved. Once again, we're Stacks on Stacks, and we thank you for your time.